Yeah, okay, this is easier to see. Okay, so Vx is 1 meter per second, and then Ez is 1 Newton per Coulomb. So then the second scenario looks like this. E is in this direction, right? Remember that the Z was the blue one, and Y was the green one. And so we have a particle moving in this direction. This time, instead of the electrical field being in this direction, it's this way. So what would we expect to happen? The object is going to be going this way with a velocity, right? Vx equals 1 meter per second, but the force experiences will be that way, in the Y direction. So what kind of path will it have? So the x and we have Fz is equal to MAZ. Fz is going to be Q times EZ, MAZ. Let's see. So then EZ is going to be 1. Q over M, we already know is 0.1, right? So then this one here is 0.1 from the earlier. So then AZ is going to be 0.1 meter per second squared. But it doesn't have initial velocity in the Y direction, in the Z direction. It only has velocity in the X direction. So we would expect its path to be kind of like gravity, right? It's thrown this way, it goes like that. So in the X direction, the equation is just going to be X equals Vxt. So there is no force in the X direction on the particle. There's only a force in the Z direction. So in the X direction, we just have X equals Vxt. In the Z direction, we have Z equals V initial ZT plus half AZT squared. So kinematics again, right, in the Z direction, but then V initial Z is 0. So then we have Z is equal to half AZT squared. Okay, and then this is X is Vxt. So this is a parabola. A classic parabola. It's kind of like you going up to the top of a building and throwing a projectile, throwing a ball like this, right? And then the ball's path looks like this, right? Projectile motion. So you're only giving it velocity in the X direction, but the acceleration of the object is in the Y direction. You see, like this. So we expect the path of that to be like a parabola. So that's this scenario. Let me see. So if I run it, now you see parabola. This is the force experienced by it. So, okay, so in 2 seconds, what happened? In 2 seconds, it's just going to be whatever Vx was, 1 meter per second times 2 seconds. So it's just going to be 2 meters. The Z direction, we expect it to travel how far? 1/2 AZ is going to be the 0.1 times 2 squared. So then 2 cancel. That's equal to 0.2 meters. And then if the Q over M ratio is 1, then the AZ should be 1, right? But now this is 0. That's okay to make 0 because there is no initial V in the Z direction. So then this is going to be 1 And there you have it. So therefore, this is 2 meters. So that means it's okay if both of them come out the same. You see, there you go. So it does match. The experimental is also, both of them are about 2 meters. You see here. You see, that makes sense that this and this are the same because A is 1. Okay, so now, what's the other thing that you can do? You can try Vx is 1, Ey is 1, Ez is 1. Okay, how about this one? Vx is 1, Vy is 1, Ey is 1. Okay, so Vx is 1. So let's try this one. Vx is 1, Vy is 1. So what does that one mean? The initial x velocity this way is 1. Vy is 1. That means it's also going to go into the board. And then Ey is 1. The electric field is going to go into the board. So what kind of path is it going to have? Of course, this is into the board like this, but I'm doing this so we can see it. Is that a parabola? Yeah, it's a parabola. Vy is 1 and Ey is 1 Newton per Coulomb. So then what's the equation in the x direction? In the x direction, you just have no forces, right? You just have a velocity in that direction. So in the x direction, you have x final is just equal to 1 times t. And that's it, no other forces, right? In the y direction, what do you have? In the y direction, you have y final is v initial yt plus half at squared, right? So then y final, the initial y is also 1, and then a was 1, right? So then you have 1 over 2, so then that's half, and then times 1 times t squared. So this is the equation in the x direction, this is the equation in the y direction, right? So if I want to know what kind of equation this represents, what you could do is substitute t is x, and then pull it into this equation. Then you have y is equal to x plus half x squared. So it's going to be a parabola that looks like that, you see? So we could put that onto Desmos, and we could say y equals x plus half x squared. Desmos. Y equals x plus 0.5x squared. So this is going to be what the equation looks like. It's just going to go like this, right? So let's see, is that what does it look like? Let's see here. Let's go like that. What does it, why does it turn back though? It shouldn't do that. So this is y. I'm going to tilt it like this so that now this is x and y. Let me see here, scale it down. Okay, now it's really zoomed in. So now just tilt Yeah, it should just go straight up like that. It shouldn't come. Oh, I don't know why it does that. Yeah, so it shouldn't come back, right? There's no. The thing is, there's no force in the x direction, so the x direction velocity should stay 1, and so it should just keep going to the right. And then the y direction electrical field is going to make it accelerate in the y direction. So it's would this be also similar to some kind of, what would be the analogy of this to gravity? You're throwing something this way and you're throwing it this way in the direction of the electrical force. Or it would be like going up on a building and throwing a ball down this way. Yep, at 45 degrees. That's what the path of this should look like. You see, throwing it down, so it would look like this, right? And then hits the ground eventually. That's what the path of this charge should look like. It goes like this. You have a component in the x direction and then a component in the y direction. And then so it just keeps going in the x, never turns back. And then the y speeds up and then hits the ground. So if this charge was going like this and there was a screen here, it would hit the screen somewhere there. Okay? Okay, now let's introduce magnetic field.